Hello. Today in this video, I'd like to talk to you about titration curves. We're going to take a look at titration curves for both strong and weak acid and bases and compare the differences between those two cases. And then finally, we're going to use titration curves to talk about indicators. Let's first take a look at the titration of a strong acid with a strong base. So the example we're going to use here is, let's say we have a solution of HCl, and that is titrated with a solution of NaOH. So I have a strong acid initially that's titrated with a strong base. A titration curve has two axes. The two axes that we're going to see here, on the left side we have the pH. The y-axis is just going to monitor the pH of the solution, and the x-axis is going to measure the volume of the base added. And we're going to think about how much this pH is going to change at different points. So initially, because I have a strong acid, my curve is going to start off very acidic, so it's going to start off at a low pH. And as I add base, that pH should rise. It's going to rise slowly because it's not going to immediately neutralize all that H+, and so there's still going to be a majority of H+ in solution when I'm slowly adding my base. And so this is going to kind of curve up here slowly. But once I get close to the equivalence point, and remember the equivalence point is where the H+ concentration equals the amount of OH- I've added, so the acid equals the base, then my pH is going to change rapidly because any amount of H+ or OH- will make a rapid change there. And so as I approach my equivalence point, I'm going to get a really steep curve there. And then finally, once I've reached the equivalence point, it's now going to become a basic solution, and so my pH is going to rise like this. And so we get kind of a classic sigmoidal looking curve, like an S, with our pH curves for strong versus strong, whether acid or base. Now, the last thing I'd want to do here with a strong versus strong curve is start labeling different parts of this curve and what's going on in each part. The first part we want to label is the equivalence point. The equivalence point is always going to be the middle of this upslope. It's going to be the place where the pH is changing the most. If you've taken calculus, it's an inflection point on that curve there. Now, what we want to see here is that to the left of my equivalence point, my major species in solution are going to be both H+ and A-, in this case Cl-, the conjugate base of my strong acid here, because that strong acid is going to completely dissociate. So I'm always going to see both of these species in solution to the left of my equivalence point. They're going to make up the majority of my solution there. Now, as I start adding base, that OH- from NaOH will react with my HCl. That's going to be a neutralization reaction and form NaCl plus water. So as I'm adding base, I'm slowly increasing the amount of Na+ that I'm going to have in solution. And at the equivalence point, I know that I'm not going to have any, or a not very significant amount, of H+ or OH- because all of this H+ will have now been consumed by the base. So my major species at the equivalence point are going to be A-, but now we're going to include M+, where M+ is the metal of my base. So in this example, over here I would have H+ and Cl-, but here I would have Cl- and Na+. So notice that at the equivalence point, most of what's present is my salt that's formed from my neutralization reaction. Finally, past the equivalence point, I'm now adding NaOH, and so my major species past the equivalence point are going to be M+ and OH-, and there's also going to be a lot of A- present as well. And so those major species I'm going to see after my equivalence point, and this makes sense because now I have a lot of OH- in solution, and so that's going to make my solution very basic. Now, this type of curve will work for a strong base titrated with a strong acid. It'll be the same thing. So let's say instead I titrated NaOH with HCl. The only major difference with this curve here is that instead of starting at a low pH, because I'm starting with NaOH, I'm now starting with a high pH. And so I would be able to draw a curve that looks like this for a strong base titrated with a strong acid. Now let's go ahead and take a look at how weak acids and weak bases might look a little different. So for weak acids and weak bases, the only major difference here is going to be the shape of the curve and the major species at each of the points. And the reason why these are different is because in my neutralization, I'm actually making a buffer solution. So let's consider, as an example, the titration of a weak acid, which is going to be HC2H3O2, our acetic acid, titrated with NaOH. Now, if we go ahead and label our axes, this is our milliliters of the base that's added, and this is our pH. Once again, because it's a weak base, it's going to initially start off at a fairly low pH. Not quite as low as you would have for a strong acid, but because it's a weak acid, this HC2H3O2, we're still going to have a low pH there. What I have to remember is that when I do this neutralization reaction, this is going to react here and form a salt, NaC2H3O2, plus water. I'm making the conjugate base of a weak acid in solution, and that conjugate base is slightly basic. And so I'm producing a buffer system as I do this. So the curves for these are actually going to start slowly level off for a second there as I add base, because I'm producing a weak base in solution, and that resists the change in pH from my NaOH. I've made a buffer solution as I add it. But then I can overcome this buffer solution as I add even more base. It's now going to go through an equivalence point, and then finally it's going to level off at a very basic solution. Now, what we want to see here are a few new features. We can still see the equivalence point here. That equivalence point hasn't changed, and that's still at the center of my pH graph here. But the new point I have is this point right here. So where this curve changes and kind of flattens off, where the slope is going to be 0, we're going to call that the half equivalence point, or the midway point. And this point is special for two reasons. It represents the point where I've added enough NaOH so that the concentration of my acid in solution is equal to my concentration of its conjugate base in solution. So there I would have just as much HC2H3O2 as I have C2H3O2. Like we know, the best a buffer can be, where it has its maximum buffer capacity, is right when the conjugate acid and base are equal. That means that this pH right here, if we drew a line over there, is equal to the pKa of that weak acid. And so using a titration curve, we can easily see the pKa of a weak acid, because that's going to be right where it levels off during that curve before it slopes up to its equivalence point. Next, let's take a look at the major species at each of these points. And so before you get to your half equivalence point, our major species is going to be slightly different than we saw with the strong acid. The strong acid and strong base, our major species was H+, because this thing completely dissociates. For here, this is not going to completely dissociate, and so our major species in the beginning is going to be HA. HA is going to be the dominant form because it doesn't dissociate, so the weak acid is going to be there. Once I get to our equivalence point, our major species are going to be HA and A-. These are going to be equal. But the other major species we're going to have here as well is going to be our metal. And the reason why is because for every A-, I'm going to have one Na. These are going to form our salts, and so my major species there are going to be HA, A-, and our M+. Then finally, coming over to our equivalence point, this is where we've now neutralized all our acid. So there's no more HA in solution. And so now our major species are A- and M+. Once again, we see that we've now formed our salt here at the equivalence point. Well, finally, past the equivalence point, we're still going to have A-, we're still going to have M+, but now once again, we've added OH- from our strong base in order to produce this high pH. So the only major differences are what happens before and the addition of this half equivalence point from our weak acid. Now, one last thing to mention here before we take a look at bases and polyprotic acids is where this equivalence point actually is. You'll notice at this equivalence point, I have a major species of A-, and that A-, because this is a weak acid, is weakly basic. And so this equivalence point is going to occur at a pH greater than 7. It must, because that solution is going to be slightly basic due to the A-. Contrast that with our strong acid we had on the previous page. Here, our equivalence point should have occurred directly at 7, because A- and M+ are the conjugates of strong acids and bases, and so they don't react with water in solution to produce any significant amount of H+ or A-. And so one major difference between the curves of strong versus strong and weak versus weak is now my equivalence point is no longer at pH of 7. For a weak acid and weak base, weak acid and strong base, that equivalence point is greater than 7. The other major difference you want to see between the curves of weak acids and strong acids is the presence of this buffer region. If you look here at our table, you notice that the pKa, you can see, this one has a Ka of -10, and so that buffer region occurs right about a pH of 10. We can read directly off that graph, but as that pKa gets larger and larger, the Ka gets larger, the pKa gets smaller, it gets closer and closer to looking like a strong acid. And notice the strong acid doesn't have this buffer region. It does not have that sloping down and then back up that we'd see from a buffer there. So that's one major difference we're going to see. The other types of curves we want to look at are what happens if we would have a weak base titrated with a strong acid rather than a weak acid titrated with a strong base. The major differences here are going to be that we're going to start again at a fairly high pH because now we have a weak base in solution. So here's our weak base. It's going to start up here at a fairly high pH. Once again, we're going to see it kind of slope down actually initially and form a buffer region there, and then come down, and then go off and level off at a low pH because now we have the presence of our strong acid in solution. And so the only difference there is that that curve is flipped. The final type of thing that we could see is what happens when you have a polyprotic acid. If you have a polyprotic acid, or an acid with multiple pKa's, if you take the look of the curve of a polyprotic, and we're going to say it's a weak acid, a polyprotic weak acid, those curves will have multiple buffer regions because each of those protons can have a different Ka. And so we might see a curve for a polyprotic that may look like this. Here on this graph, we can see that our equivalence point is still right here, and it's still going to be at a high pH. pH greater than 7, because for a weak acid, the equivalence point is going to be greater than 7. But I also have another equivalence point. And this equivalence point could be higher or lower, depending on the specific acid, but it's in between these two buffer regions. And these two buffer regions represent the pKa of the first ionization of that acid and the pKa of the second ionization of that acid. So if you have a diprotic acid, like this one here, you would expect to see two buffer regions and then two equivalence points, depending on what you see. Finally, the last thing to mention is where the equivalence point is for a weak base versus a weak acid. For a weak acid, at the equivalence point, there was a significant amount of conjugate base there, which made this pH slightly basic. Here, for a weak base, we would expect that there would be a significant amount of conjugate acid at that point, and thus, this pH should be slightly lower than 7. And so for a weak base, the equivalence point is going to be lower than 7. Finally, let's go ahead and take a look at how indicators play a role in these titration curves. Indicators, as we know, are used to detect pH changes in a solution, especially during a titration, to determine whether a titration has reached completion or reached the equivalence point. One important thing to know then is that indicators themselves are also weak acids, and so we can represent the equilibrium for an indicator. We'll say our indicator's In. With an H, it's going to be in equilibrium with H plus and IN minus. And this particular equilibrium will have some Ka, and because most indicators are weak acids, they're going to have a pKa. That pKa determines the range of usefulness of that indicator. For example, the pKa of phenolphthalein is around 9.3, and so you'll notice that 9.3 occurs right in the middle of the range when it changed from being colorless. In this case, they say red, though a lot of people will say that phenolphthalein looks pink. That determines where it's best to use phenolphthalein. We would want to use phenolphthalein when the equivalence point of our titration is close to that pKa. And so we use indicators with pKa's close to our equivalence point. If you look down at this graph here, you notice that this titration curve is for a weak acid titrated with a strong base. The reason why we can know it's for a weak acid is because we see a significant buffer region, and in the middle of that buffer region, the pH is equal to the pKa there. Now, using phenolphthalein looks appropriate for this titration because for a weak acid, the equivalence point is going to be slightly basic. Here it's kind of indicating that that equivalence point is right around 9, very, very close to the pKa of our indicator, phenolphthalein. So we'll see a nice color change right when we reach the equivalence point. Bromophenol blue, however, would not be a good indicator to use here because it's changing its color right around here at the beginning of the titration. So that won't indicate the strength of our acid because it won't correctly indicate our equivalence point here. So we always want to choose an indicator that has a pKa close to the equivalence point of my expected titration. So for a weak acid titrated with a strong base, we notice it's a slightly basic indicator. So if you looked up at this chart, indicators to the top right of this chart will work better for a weak acid with a strong base because those ones will turn right around a weakly basic pH, whereas the ones on the bottom of this chart would work well for titrating a weak base with a strong acid because the equivalence point for that titration tends to be slightly acidic. Today we've learned about strong acid and weak acid titration curves, as well as taking a look at a little bit of indicators. Thank you so much for watching. Have a great day.